is the new conference of our Applied Mathematics webinar. Our speaker today is Sabrine Chebbi. Sabrine had her PhD degree in mathematical faculty of Science of Tunis on asymptotic behavior and optimality of energy of certain Timeshko systems. And she was awarded of the best thesis for the Tunisian woman in pure mathematics. From September 2022 to November 2022, she had a postdoc in Institute of Mathematics in the Czech Academy of Science on fluid structure interaction. And during these 2 last years, she had a postdoc position at the University of Tubingen in collaboration with AIMS in South Africa on a project on multi-armed bandit theory and application and in communication and communication networks. The talk of today concerns the machine learning tool for solving beam model of Timoshenko system with thermoelasticity. Thank you, Sabrine, for accepting our invitation, and you have almost 50 minutes to present your work.
Thank you so much for this nice introduction, and also thank you for the invitation. So it's as well a great pleasure for me to present my work. So today I will be talking about machine learning tool for solving beam model, more precisely for solving Timoshenko system with thermoelasticity. So this talk is based on a joint work with my 2 colleagues from AIMS South Africa, Joseph and Professor Babakar, and also with my PhD supervisor, Professor Makram Hamouda. So the outline of my presentation is as follows. I will start by presenting or explaining the intuition behind this machine learning tool, which has been used to solve PDEs, more precisely physics-informed neural network, or shortly PINS. Later, I will recall some theoretical result for the Timoshenko system that has been obtained in previous work. And later, I will present the experimental result that we obtained for this system using PINS. And finally, I will end my presentation by a conclusion. So as a motivation, we all know artificial intelligence. So it's about having a machine which is able to think and to make decisions similar to the human being. And this AI has achieved a remarkable success in both academia and also industry. And let me cite some example like AlphaGo, which is the company DeepMind has proved that create an algorithm which is able to play like a human being and also to win in front of champion of this Go game. And also I will cite ChatGPT, which we all know what he can do, and also other application of AI that has facilitated our life. So in this branch of AI, we have machine learning. And machine learning is about having an algorithm which is able to predict a solution, either based on the interaction with the environment or based on a data that we give it to it. So more precisely, I will be talking in this presentation about physics-informed machine learning, or with abbreviation PML. So it's about having an algorithm based on a data, but also including some information coming from the physics law. And where we say physics law is about, we know that all the physics phenomena are presented by partial differential equation. So it's about a method or a tool in machine learning that solve PDE and that take into account the information coming from the physics law. So the question is, what is PINS, or what is this PML, or what is the physics-informed neural networks? So the first part in PINS is based on an artificial neural network. And in deep learning, we have two big categories of neural network, the fully connected neural network and the convolutional neural network. So what I mean by fully connected neural network, that means all the layers are related or connected to each other. So the neural network is represented by this expression in which we have X is the input. So first of all, we take the input, we multiply it by a weight matrix, or we do a linear transformation of this input, and then we apply a nonlinear activation function, which is sigma here, and we obtain the output of the first layer. Then this of the first layer will play the role of input for the second layer. So that means we will repeat the same process by having a linear transformation, and then we apply sigma, which is a nonlinear activation function, and then we obtain an output of the second layer, and so on and so forth. So this process is repeatedly for n number of layers. And the optimization problem for this case is given by the fact of minimizing a loss function, which is some function of the neural, is some function of the neural network. So the question is, how can we use this structure in order to solve a PDE? To answer this question, we have two approaches. The first one is the supervised approach. And what I mean by a supervised approach, the fact that at the first step, we need to use another solver. This solver could be an analytical solver, that means we have an exact solution, or it could be any other numerical method that generates a data set of solution. So this is the first step, and then we need to train the neural network in order to learn the mapping from X to UX. And then the hope is once we have a new input, we are able by this neural network to predict the solution, which is very near to the actual solution. So in this approach, we are faced to a first step, which is having a solver. And in some cases, we are not necessarily sure that we have a solver, and it could be exponential, very expensive computational to obtain this solver. So not necessarily for all PDEs, we can generate this data set of solution. So the question is, could we replace this approach by another approach in which we will not use a solver, or we don't have any knowledge on the actual solution? Well, the answer is yes, by an unsupervised approach in which we will not need to have a solver, but we only need to select random collocation points. And those random collocation points could be at in the domain of our PDE, where the PDE is defined at in the domain, interior of the domain, and also in the boundary of the domain. And I will explain this more details of this in the later slides. And the goal is to solve a PDE by minimizing a single loss function, which is I define it here as a loss between the neural network and the solution. And also I will add something, I will call it physics loss thanks to the PDE residual. And I will explain what is this exactly. So in this approach, we don't need any knowledge on the actual solution. And in a few words, so PINS is an unsupervised approach that use the information coming from the PDE itself to predict the solution. So as you can see in this schema, we only have a collocation points. We train the neural network, but while training the neural network, we will obtain an output, but this output need also to be in coherence with the physics information or the PDE, and then we would like to minimize a loss function. So someone can also ask why minimizing a loss function, such a loss function, give me an approximation to a PDE solution. And this question has been investigated in this paper, in which they obtain a theorem that says, if we have the well-posed PDE, a very general PDE of the form A of xu, A is a differential operator defined on omega, B is a differential operator defined on the boundary of omega, and we define a loss function as follow. So the theorem says once the loss function is very small, that implies that the neural network is approximating the solution. Okay, so I think that now we have the whole image about the pins or about the physics-informed neural network. So we would like to use this framework to solve one of the general systems, which is also based on a physics phenomenon, which model the deformation of a beam, which is a mechanical structure. So so the deformation of a beam is based on a theory of Timoshenko, which take into account the shear deformation. So in this case, we have two main unknowns, which are phi here represent the displacement of the beam, the displacement vector, psi represent the rotation angle, and also we would like to have a more general system that take into account other factors such that the temperature and the heat flow. So mathematically speaking, we have four partial differential equations, which are coupled, and also we have ρ1, K, B, ρ2, ρ3, etc. are considered to be a physical parameter, and they are considered to be positive constant. So for this system, we don't really know the exact solution. So what we usually know is to apply finite element method, or either volume method, or finite volume method, or finite difference method, in order to do the full discretization on time, on space, and then approximate the solution. So this is what we usually do. So in our talk, we would like to apply the pins in order to approximate the solution. So for this system, we also add another information at the for the boundary. So we take a mixed Dirichlet-Newman boundary condition, and also we add initial condition in order to ensure the uniqueness of the solution. So this system has really attracted the attention of many research in the sense of trying to study the stability of the system. That means we need to associate to the solution of the system a quantity, or the norm of the solution is represented by the energy, and we would like to see when time goes to infinity how the energy will behave. We would like to characterize the behavior of the energy. And most of the results that related to the stability of the Timoshenko system are based on the stability number, which is defined as follows. So as you can see here, is a relationship between all the physical parameters that we have in the system. Okay, so I will recall some existing and unique, the existence and uniqueness result associated to this Timoshenko system. So for an initial condition which belongs to some specific space, Sobolev space, that takes into account also the boundary condition, the system has a unique strong solution which belongs to this space. So once we have the existence and uniqueness of the solution, we can associate to this solution a quantity named the energy, which defined by this expression. And we would like to see what are the criteria of this function. We only do the first derivative with respect to time of this quantity. And just by multiplying the first equation formally by phi t, psi t, and theta and q, we will obtain that the first derivative with respect to time of the energy is equal to this negative quantity, and thus confirm that we have a dissipation of the energy. So when time goes to infinity, we probably need to find that the energy will go to some equilibrium state. Okay, so those what we have for the theoretical. And remember that we keep in mind that we don't have an exact solution for this system. So we would like to use the framework of beans in order to approximate first the solution, and later we would like also to use this tool in order to know more about the energy. So here I will just explain more what is beans adapted to the Timoshenko system. So our input here, we have X and T. So X is the space variable and T is the time variable. And then, as you can see here, I have presented only one layer, but this doesn't mean that we took, for the algorithm, we took only one layer. I will precise later how many layers we...
Sabrine, can I just here for the input X and T, just one position, or you mean a set of positions of X on your collocations point that
yes.
you...
Sorry? Okay, if I will understand it, you are asking if we are taking one point or we are taking a set of points.
Exactly, yes.
We are taking a set of collocation points corresponding to X and also corresponding to time. Because we cannot just... Yeah.
And it's the same for T, for several points for time too?
Yes. In this case, we took the same number of collocation points for X and T. For example, yeah, in the algorithm, for example, you can choose to choose the collocation point which follow a uniform distribution or any other distribution.
Okay. Thank you.
And then, thank you. Thank you. Please feel free to interrupt me if there is something which is not clear. Thank you so much. Okay, so here we have those input, we have the X and time, and as I said, we have a set of collocation points, and then we have the activation function, and then we have the output. So the output, because if you remember in this system, we have 4 unknowns, phi, psi, theta, and q. So here, what we hope to obtain as an output are the 4 unknowns of the systems. And then here, we would like...
Same question. It's your 4 variables in each point of the collocation points.
But actually, yes, exactly. But actually, it's not discrete in a discrete way. Like the result of a neural network is a function, not in the like in the traditional numerical method. Like we are obtaining a vector, for example, of solution. Here we are obtaining a function.
How you can obtain a function, a continuous function?
Yes, we will obtain a continuous function because like you are taking a set of collocation points, but when you apply, you remember that we will multiply it by do this linear transformation.
Yes. This is clear, yes.
Okay. So we obtain a continuous function. This is the neural network. And then if we come back to the numerical traditional method, so we need to take the derivation with respect to time, x, etc. We need to approximate the derivation. But here we already, as I said, the neural operator give me a function, so we are able directly to use automatic differentiation and then obtain and then include the PDE of the system. So this step is only is directly using the neural network result and include the information coming from the system, and then we hope to have a total loss. I will explain. I will give the exact expression of the total loss, and once if the total loss is really small, so we are done. If not, we need to repeat the process by modifying something in a neural network, like by either increasing the number of layers, either to change the activation function, either do some modification or changing the distribution of the collocation points, and hoping that we at the next step, training, we will have a total loss which is small enough to be able to predict the solution. Good. So what we will, so mathematically, or what we will do in order to have this is, first of all, we need to select a set of n collocation points. in the interior domain and at the boundary. And then we need to approximate the solution by a neural network, which is here represented by Psi, X, T, and Xi. So it's the parameter of the neural network. And then we need to make this neural network also take the information of the PDE. And this is why we introduce or define the residual. So the residual is about taking the PDE for the neural network. Sorry. And here is exactly the same PDE, because in the system, we have the first equation is equal to 0. So if not, we will have, if we have, for example, a source term, it needs to be minus this source term. And those are the residual for the neural network. Once, of course, those are associated to the PDE 1, 2, 3, etc. And also, we need to have a residual associated to the boundary condition and to the initial condition. And we know that the exact solution of the system need to satisfy that all the residual are equal to 0. That's why we would like to define the mean square root error, which is taking 1 over n, and n is the dimension of the set of collocation points associated to time, to x and time. And the loss function, the total loss, is about having the sum of all the mean square root error. Good. Okay. So once we have this framework, we are able to test it in, and we are able to obtain experimental results. And that's what we did. So first of all, remember that I told you that for the Timochenko system with thermoelasticity, we don't have an exact solution. So how we can test the performance of the pins if we don't have an exact solution? So what we did is, first of all, to the parameter ρ1, ρ3, theta, and etc. are equal to 1. We take the domain is from 0, 1, and t belong to 0, t. And we impose F1, F2, F3, F4 as the source term, which are given. And once we give F1, F2, F3, F4, we are able to determine an exact solution or construct an exact solution associated to this system. Okay, and we assume it for facility just to that we have a Dirichlet boundary condition, but of course we can do a Newman mixed Dirichlet boundary condition. Yeah. So the exact solution could be determined explicitly for this case. So we know that the exact solution, if we take F1, F2, F3 as this form, we have an exact solution which is equal to this one. Okay, so we go to the algorithm, we go to coding, and we construct a neural network, a fully connected neural network using PyTorch. And here the feature of the neural network is we have 2 input neurons and then corresponding to time and space, what I have explained in the figure, following by 5 hiding layers. So in this case, we took 5 hiding layers with 100 neurons each. And then the output should be composed by 4 neurons, which are the unknowns of the system. We take a non-activation function, which is the hyperbolic tangent, and also we train it using Adam optimizer. We train it the data set considering 300 random selected collocation points, and then yeah, we train it for 10,000 epochs for Google in Google Colab for GPU. Okay, and that's what we obtain. So first of all, we plot the total loss, which, as you can see here, have a highest value, which is equal to 10 minus 2, and as a less value, which very near to 0. So we are sure that for this case or for this system in which we know the exact solution, we have a total loss which is very small, And if we would like to see the loss coming from the PDE separately and the boundary condition and the initial condition separately, we can plot each of them separately. And we can see that all of them are going to, are decreasing and going to value which is very small. So while we maybe cannot see the exact solution, because we took that the exact solution are all equal to the same function, and we plot the result from the pins, and we see that all of them are having the same behavior. And we wanted also to plot the error coming, or the difference between the pin solution and also the exact solution. That's why we plotted the relative error and also the L2 norm error. And we find that all of them give us a very small error. It was only just to test the performance of pins when we have an exact solution for the Timoshenko system that we constructed. Later, we just take this framework or this code for the pins and just like eliminating the source term, and we would like to see the behavior of the solution in this case. So we used the following parameters. We took the number of collocation points for x and t equal 300, for a time final time equal 13, and the number of iteration is equal to 10,000. And if you remember at the beginning, I say that the research has been interested in Timoshenko system in the sense of trying to see the stability of the system. So here, sorry for coming back, but I need to show you that we add a non-linear damping term to the system. So we know that even the coupling with the temperature is alone can produce a damping to a system, but also we add this linear damping in order to see later the behavior of the energy with the presence of this linear damping. So case one, if we assume that we don't have an additional damping term, so for mu equals 0, and for xc, which is the stability number, different also than 0. Okay. So this is the first case. Yes. And the second case, we take that for xc equal to 0. So the fact of xc equals 0, that means we took a very specific value of the physical parameters. And this is what we obtained. So this is one, before we couldn't even obtain or see the behavior or know the exact solution of the Timoshenko system. Now, by this method, which is, we don't need to do the discretization, we only apply a neural network and interpret the information coming from the pins, we are able to determine the behavior of the solution when time goes to infinity. And this is what we obtain. So each one of them are corresponding to unknowns of the system. Okay, and also to be sure that we have a good prediction of the solution, so we plotted the total loss, which is almost equal to 0, and those are the training loss. That means the PDE loss, the initial condition, and the boundary condition loss for different cases, because I took the case when mu is when xc equals 0 and when xc different than 0. So all of this is important because the fact of having explicitly what we already know as a theoretical is really make the results visible for us. Now we would like, once we have the solution, we know that we are able to have the energy. So here somebody can ask me why we are approximating this functional while we could again use the neural network, like, because the neural network give me directly automatic differentiation, and we will not be we will not need to discretize the points, the domain. So here I didn't want to use again neural network, but I just would like to approximate the energy by this expression, which is a quadratic, by the expression of a quadratic form. We took a quadratic point and we approximate the integral functional of the energy, giving this one, this expression. But here, this phi tilde is the result of the pins, like this is the pin solution. So the algorithm of the discrete energy of pin solution of Timoshenko is about, first of all, compute the pin solution, and then I use the finite difference method in time and in space to compute the derivation of the pin solution obtained in the as a result of pins. And then I wanted to see the evolution of the discrete energy based on this pins prediction of the solution. Okay, so what we obtained is the following. So when mu equals 0, the fact that I'm testing over the term, the damping term, so for mu equals 0, that means we only have the direct damped system, and we took rho 1 k, we took c equals 0. In the theoretical result, we have that the energy will go to a stable state, but not necessarily equal to 0. And this is what we obtained by using the pin solution. So we plotted the energy as a function of time, and we remark that at the end, the energy will not reach 0. It's equal to some constant, which not necessarily exactly 0. And this is this is what explains the non-conservation. First of all, we have the non-conservation of the energy, because if the derivation of the energy was equal to 0, so the energy is equal to a constant, while here the energy is a decreasing function. So that's confirmed the non-conservation of the energy. And then we have also the strong stability, that means the energy will, at time, for example, starting from time 4, the energy will conserve a constant value, which not necessarily equal to 0. Okay. Later, we took theta 0 of 0 equal to 0. If we take it equal to 0, so in this case, the energy will reach the value of 0. So it's a decreasing function, but also it will decay, it will go to 0 when time goes to infinity. And we would like to see the behavior of the energy, like to study the decay rate. Either it is exponential, either it is polynomial. So we plot ln of the energy as a function of t, and we find that though this linear line is collecting the number, is collecting the behavior of the energy from 0 to 5. As you can see, this decreasing is exponential decay rate of the energy. So we are able to explicitly see how the energy will decay to 0 when time goes to infinity. Same for if we add a linear damping. So if we add a linear damping, that means for mu equal 1 and c equals 0, theoretically, we have also an exponential decay rate of the energy. And that's what we saw it by using also this machine learning tool. So the energy, first of all, decreasing and goes to 0 when time goes to infinity. And also we have this exponential decay rate for linear damping. Okay, so if you, so for traditional or traditional numerical method, if we include a nonlinear damping term to the system, in this case, we need not necessarily a normal discretization or an approximation of the solution of the term could be easy to obtain. So in this case, what we while using pins, we just need to include this information to the second to residual associated to the second equation. And by this modification, we can obtain a new solution or generate a new solution using pins to obtain the approximated solution. And then we can directly, I just would like to come back to this schema in which, so once we have the solution of the PDE, an approximation using pins, we just go and take the collocation point and the solution coming from the pins just to do the discrete energy. That's what we did. Okay, so here we only took a different value of x, which is the stability number, and a different value of nu in order to specify the type of a damping that we included to the system. So here we plotted T as a function of ln of the energy, its exponential decay rate, while here we know that if xc is different than 0, then we will not have an exponential decay rate, but rather we have a polynomial decay rate. That's why, sorry, plotted ln of the energy as a function of ln of T. Same, here we took a nonlinear damping term. So the energy is a decreasing function, but also we characterize the decreasing of the energy by logarithmic decay rate. So we plotted ln of the energy as a function of ln. Okay, so finally, as a conclusion, so what we did is we used the framework of pins in order, first of all, to approximate the solution for the linear or the non-linear damped Timoshenko system. And then we took this approximated solution in order to see to characterize the behavior of the energy associated to the pin solution. We took a different type of damping terms, and also someone could ask how pins has proved a good performance for obtaining a solution or approximating the PDE solution. But also the other part of theoretically study of this pins method in the sense of convergence and error remains relatively restricted, and we would like to go further in this direction, and also why not study the convergence and the error of pins. Okay, this is a list of reference that I used in the paper, and in those reference you will find some of them speaking about theoretical result of the Timoshenko system. Some of them are using pins for other kind of partial differential equations. And also the last one here, you can find that pins has been also used for Timoshenko system, but for 2 equations, and also as considering it as an inverse problem, not forward system. So and thank you for your attention. Am I on time or? Okay, thank you.
Okay, yes, thank you, Sabrine. Okay, do you have questions? Is there some questions, please? Okay, I have some questions.
Yeah, sure.
Can you come back to the picture when you explain your neural network, because really there is something that is not clear.
Okay.
I think
here.
I think that there is a confusion, and if you say that you need to make automatic differentiation, I think that your input is not the collocation points, but only one x and one t, and like this, your output is the 4 variables given on X on NT, but only for one X and one T, not for, on all the collocation points. Is it true? Can you tell me if it's what you
Yes.
want to say, or there is something else?
No.
Because what you said before was not clear for me.
Okay, it's exactly what you say. The only thing that the fact that I'm taking at first time, I'm taking a set of collocation points, that means I will test the neural network for each point of this set of collocation points.
Okay.
Like
okay.
for each, yeah.
Okay. Okay, it's clear now. Okay.
Okay. Good.
Okay, thank you. And can you please just come back to the loss function and explicit it? Okay.
Yes.
Okay. Yes, thank you. Then here, this is your. Okay, you have eight loss functions. Okay, that are a mean value of on all the collocation points, and the residual. What is the expression of the residual?
It's about taking the neural network but apply it to the PDE.
Okay.
The fact that
okay,
it's the automatic.
It's just okay. It's just you apply your operator on the neural network.
Exactly.
Okay. Okay, it's clear. Okay, thank you. But can you give your slides on the results? The first slide on the results. Yeah.
Which one? This one?
Yes, this one. Yeah. Okay. Here, the first one. Then you say that you have the three loss functions on the PDE, the boundary condition and initial conditions. Okay. But what we see here from the iteration 9,000 to 10,000, it's almost the same value. There is no decreasing of, okay, it's oscillating, but how do you explain this? But,
okay.
but do you have a plot of the first iterations before 9,000?
Yes, we have it. But like, if we would like to see, because if for pins you are not like taking care of the first value, even if the value are so big, what is important to you is to see how is the behavior of the loss function at the end. Like, for example, I could stop from 9,200, for example. I can stop there. Yeah, and it will be the same interpretation. The fact that the loss function is decreasing is already good, but like the less value that you obtain, if it is near to zero, it's confirming that we have a good approximation of the energy. Because you can see in the optimization problem, we have many losses to be minimized. We have the loss associated to the PDE, the initial condition, and the boundary condition. It could be that the neural network minimize better the PDE than the initial condition, or better the boundary condition better than the PDE.
Mm-hmm. Okay.
So if, for example, if you can go to other article, you will find that they add another weight, like another constant to each of the loss function in order to stabilize this. That means in order to find a minimum a minimizer that minimize all the losses in the same way.
Mm-hmm. Mm-hmm. Okay. Okay. Is there other questions?
Yes, please, Nabil.
Yes, Rafiq.
What about the number of steps needed to obtain a loss function less than epsilon? Maybe in slide 13 or 15.
Yes.
You repeat the algorithm until you obtain a loss function less epsilon. What about this number of steps, this number of repetition of this procedure to obtain a loss function less than epsilon? Is a random variable or is random?
Yes, if for example, if I understand well your question, if you remember when I was explaining the beans framework, I said once if we, for example, start by 2 hiding layer, and we do the same process and we obtain that the loss function not necessarily very small. So we need to come back to modify this neural network. And by modifying this neural network, it's randomly. We need each time to either modify the number of hiding layer, either modify the activation function, either modify something, or even the optimizer in order to obtain this minimum loss function, minimum value of loss function.
Okay, and the choice of the input is a random choice, or the choice of X and T are random?
Yes, yes. So for example, the framework or the setup that I put it here not necessarily will be working on another PDE. For each PDE, we have a general framework of pins that I explained it, like you have input, output neural operator, physics-informed neural network, like physics-informed, and also we have the automatic differentiation, but not necessarily this framework using this variable can be work for another PDE. It could not work. Like each PDE have a specific parameter that give us a small value of loss, total loss.
Okay, okay. So if you choose some X and some T, and you find that your loss function is larger, is not small. So you have to choose again another X and another T. You cannot use the last choices to solve the best X and T to have the chance to obtain a smaller loss function.
You can conserve the collocation point, but you need to add hiding layer or to modify the number of neurons.
Okay, okay. Okay, so you are not sure how many steps you need to obtain your desired loss function.
No, we don't. No, we don't know this. And this could be one of the questions that while studying the convergence of pins.
Okay, okay, okay.
Thank you so much for the question.
Thank you for you.
Okay, I have one question.
Okay, okay, good.
Do you finish, Rafiq?
Just, can you go to slide, next slide, 16?
Yes.
For the convergence. So for the first figure, can you have sometimes a larger loss function, and after you have a small loss function, and after you have larger loss function, it depends on what? On the choice of the initial condition?
Not necessarily, but what I really know is the fact that we have some noise while we are training the code. So the fact of having exactly a decreasing loss function is not like the ideal way, because seeing oscillation in the loss function is the normal visualization of the loss, because we cannot like obtain decreasing function. This is what we know, what I know. Like the fact it's due to the noise, I don't know, in one step or in another.
Okay. Okay, thank you, Sabrine, for this nice talk and for your answer.
Thank you so much. Yeah.
Just one more question, please. When you described your neural network, you say that you have 5 hidden layers with 100
yes.
neurons on each layer. And
Yes.
do you make a sensibility analysis to see if this is optimal, or if you can have I don't know, perhaps معناها the same results with less neurons on each layer, or do you try other values for this hyperparameters?
This is a great question, but it is really conservative for the fact of studying the convergence of beans. Because in my case, of course, we tried other, but we did not take care of this like the optimal number of neurons or the optimal number of hiding layer that we need to use in order to have an optimal result. We did not investigate this, but it's a great question to be studied at the next step.
Okay, but even if you don't make an optimal analysis, do you test other values, and
Yes.
results do you have?
Yes.
Do you have same results, or better or worse results?
It's for sure, like, we did not at the first time obtain this good minimum value of total loss. We started by 4 layers, we started by 3 layers, we started by 15 neurons, etc. and etc. So at the end, we were able to say that those numbers are the ones who give me good performance. Like you cannot from the beginning just say a number and it will work.
Okay. And okay, I think I will stop here. Is there other questions?
Yes, Chairman. Can I ask a question?
Yes, of course.
Okay. If you can put the flow chart, I don't know which slide is it, number 7 or 6, I don't recall. The flow chart of the system, yes.
Okay.
The flow chart, not the one more.
One more? This one?
No, number 7. Number 7.
Okay, number 7, this one.
8, 9, I don't know.
Here.
The flow chart, this one. Yeah.
Okay. Yeah.
So if I understand the logic of the system here, so you calculate the total loss based on losses, 8 losses that you calculate between the neural network and the physics of the equations. That's my understanding. And then you check if that error is less than a tolerance. So where is the optimization here? I'm confused. How do you use this loss?
Okay, so this loss is depending of the parameter of the neural network, right? Which is X.
So the only like in your iteration, the only optimization is within the neural network itself.
Exactly.
So how you then my problem is that you are not using the information that you're connecting the neural network with the physics. You are not using where this error is going.
We are using them, like, as I said at the beginning, we are taking one single loss like that, take in all the constraint together. So you cannot, like, we are, if according to you, we are just taking the loss function that is the difference between the neural network and the solution, which is not the case. So we have this loss, and also we have the other losses to obtain this total loss.
So the loss, the loss function that you are using is included in the neural network functioning.
Yes, because
so it's part of the neural network. So it's not completely.
Exactly.
Okay. Yeah. Question number 2. So here you are solving a mathematical problem. Now I will talk from engineering point of view. Suppose that your input comes from experimental data.
Okay.
So they are necessarily corrupted by noise. Do you know what is the stability of your system in the presence of noise?
Okay,
because in practice, this is what we do. In practice, we don't solve the problem for the sake of solving it. We solve a problem. Usually, we have data and we solve. So you can have a system that works perfectly right at no noise, but can be completely erratic with the presence of noise.
Okay. If for example, I will try just to think from your point of view. Okay, now if we have data, so for example, for the inverse problem, if you
no, Sabrine.
Yeah.
It's just here, it's very easy. You have some parameters for your model.
Yes.
Imagine, instead to have constant parameters, you have just these constant with some noise. Okay. And the question of Fawzi is to see if it's stable, okay, with respect to these to this noise, okay, to the variation.
I think you summarize it right.
You understand, Sabrine?
Yes, you mean the parameter ρ1, ρ2, k, and
Exact. Yes.
We did not do that, but
yes, it's a good question. You can
Yeah.
Of course you can, and you can test it very easily. Okay, you have the software, you can test it and see if it's without studying it theoretically. Okay, and you can do the theory after that. Okay, but tomorrow you can test this. Okay.
Okay, good. Okay, yeah. If I will understand you, you will need to just modify, like do some variation of those parameters.
Yeah.
Okay. Yeah.
Thank you.
Thank you so much. Thank you for your question.
Okay. Is there other questions? Okay. Thank you, Sabrine. It's very beautiful subject. It's a hot topic, of course, and it's why we have so much questions. Okay, and probably I will contact you to ask you more questions.
You are welcome. You are always welcome.
Okay, thank you everybody
Thank you
to be
so
with us, and see you next week for another talk. See you.